update that in light of the data. That is the most general possible model for data that have an exchangeable character. And as a by the way, if you think through it, the binary one is a special case of this thing here, because knowing theta in the binary case is the same as knowing the CDF when all you have is a dichotomous outcome. What would it mean even to have distribution when you drew from it? Each individual draw, instead of being a point or a vector or a matrix, was actually an entire function. Well, what do CDFs look like? The only two things that are the restrictions about CDFs is that, actually I guess there's three. In the limit as you go to minus infinity, this is a CDF for some variable x, let's say, and this is f of x. In the limit as x goes to minus infinity, you have to go to 0. In the limit as x goes to plus infinity, you have to go to 1. And in between, the function has to be monotonic, non-decreasing. So it's allowed to have flat places, but it can't ever go backwards. It can't ever go down. So that is an example of a CDF, for example. This is about where x is something that lives on the whole real line. So literally, what a distribution would be that had as its outcomes entire functions. Imagine sampling from it. That might be the first one. The second one might look like that. The third one might look like this, much flatter. And so you can imagine building over time. Let's see. It sounds like this is cutting in and out a little bit. Sorry about that. And building up over time. The noise while I try to get this to be in a good place. You can imagine building up over time a kind of an envelope, right? It would start. What would start happening is that if you were to cut the thing in the other direction and imagine having a frequency sort of sense coming up out of the page, it's almost like things like little normal curves across those different function possibilities would start appearing. And down at this end, they wouldn't look like normal curves. They'd look skewed because they are jammed up against 0. And up at this end, they'd look skewed the other way because they're jammed up against 1. But you can sort of imagine that kind of thing. And it does turn out to be that there is a mathematics that allows you to sample from CDFs. So the first person to work on it carefully was around the year 1970, a wonderful statistician at UCLA named Tom Ferguson. And we will hear more about him later on when we talk about Bayesian non-parametric methods. So that's hard work. Instead, usually, is they pretend that some standard parametric family that they're used to is a good approximation to putting a prior on all possible CDFs. So you just make a big pretend and you say, well, data are going to be Gaussian. I don't know why we're cutting in and out so much. Ahead of time, the data are going to look roughly Gaussian. So I'm just going to pretend that my prior on the set of all possible CDFs puts all of its mass on the normal distributions. Now, obviously, it would be silly to put all your mass right on, let's say, the normal distribution with mean 3 and variance 5. But instead of thinking about a prior that was over all CDFs, you could put down a prior that said, oh, well, I think things are going to be normal. So it's going to consist of normal mu sigma squared CDFs, where mu can be any number it wants from minus infinity to plus infinity, and sigma squared can be any number it wants as long as it's positive. That is an uncountably infinite number of CDFs, but it's nowhere near big enough. It doesn't cover all the possibilities. For instance, suppose you put that down as your prior, and then you started looking at the data once it arrived, and the data were bimodal. As you know, there is no single member of the normal family that has a bimodal character to it, right? And so that's another aspect about De Finetti's story that seems daunting. He says you're supposed to write down this prior before you see the data, and what should you do as a Bayesian if, having written it down, you notice that the prior has put probability 0 on stuff that's actually happening in the data? That would be very embarrassing. And the reason for that is something we talked about in one of the homework sets. I think I spoke about it a little briefly. At the end of homework set 1, there's this thing called Cromwell's rule. Cromwell's rule. And Cromwell's rule says that if you assume the prior probability for something is 0, then the posterior probability for that thing, given any evidence that the world might provide you with, has to also be 0. And if you assume that the prior probability on something is 1, then the posterior probability for that thing, given any evidence in the world could give you, has to be 1. So A as standing for how the data might come out, and B as standing for something related to the unknown that you're interested in. Something like your theta. I don't know why we're cutting in and out so much. Maybe, is it a battery problem? In which case, we're going to wish we had a different set of batteries fairly soon. Let me try again. So you don't know for sure what's going on. Then, oh yeah, good. So we can try that. Okay, I'm going to take a tiny break and try to put a new battery in here and see if that improves things. So. Looks like I've gotten this done, so let's try this real fast and see if we don't get feedback. How about now? Let's see if that keeps me from cutting in and out. That would be great if that was the problem. Let's try anyway. Thanks very much. Okay, so the way this is relevant to this problem here, suppose I wrote down a prior on the set of all possible CDFs that put 0 prior probability on something that actually turns out to be true in the data. For example, I put a prior down that only focuses on the normal distributions, and then the data comes out bimodal. Then, no matter how the data came out, whether it's bimodal or not, the posterior probability that something outside the normal distributions, the posterior probability of that has to be 0 because the prior probability was 0. You have no room. The problem with this observation is that in the Bayesian paradigm, strictly speaking, unless there's some way to go back and change your prior, you have no way to learn from the world. If you put prior probability 0 on something, you've already painted yourself in a corner. Formally speaking, in the Bayesian paradigm, then no matter how the world comes out afterwards, you still have to stick with probability 0, or similarly probability 1. For that reason, Bayesians try very hard not to put prior probability 0 on anything unless they think it's actually impossible. And they try not to put any prior probability 1 on anything unless they think it's absolutely certain. So you'll see Bayesians write to each other, what's your probability that you're going to go to the joint statistical meetings this year? Thanks very much. We have almost all about rights and a small number of people too fast, and that pretty well agrees with what I was thinking about how things are going. So thank you for that. Unless we have a way to go back and change our prior based upon something that surprises us in the data, Cromwell's rule says that we're in real trouble. So when Bayesians are writing to each other and they say things like, what's your probability of going to the joint statistical meetings this year? Somebody might say, my probability is 0.99, or my probability is 0.996, or some number like that. Everybody tries really hard not to say 1 on anything. And similarly, try hard not to say 0 on anything that might, even remotely, but might come out to turn out to be true. So if we're going to try to use this Bayesian nonparametric idea, then to avoid Cromwell's rule, somehow we have to be able to put priors on this space of all CDFs that in some meaningful sense don't put 0 prior probability on anything. In other words, the prior has to be unbelievably open to possibilities. And it does turn out that in technical terms, there are several different ways to do that. Although when people first started thinking about this, it wasn't so clear that was possible. But now we understand it is possible to construct such priors. And when we have the unit on Bayesian nonparametrics 4 or 5 weeks from now, I'll try to show you how that goes. So what people do instead, as I was saying here, I'll talk from the PDF again. This is the fancy way to write De Finetti's theorem for continuous outcomes, but the less fancy way is to say basically exchangeability of real valued observables is equivalent to a hierarchical model in which you think of capital F as the CDF of all the Y values in the population that you're trying to learn about. And if you knew what F was, the YIs would be IID from F. That defines what amounts to a kind of non-parametric likelihood. And then you have to put a prior on the set of all CDFs. F is in fact a kind of a parameter that has infinite dimensions, and not even just that, uncountably infinite dimensions. So it's a very, very big thing. In real practice, the way people fit these priors, the prior in capital F is nowhere near infinite dimensional because you can't really cope with an object that big. So what you do is instead the polyetry idea I'm going to show you in a few weeks breaks down to thinking about F as like one or another of a series of random histograms. And even for a data set with 2 or 3 significant figures, they never let the number of random histogram bars get any bigger than about 64 or 128. You use powers of 2 usually. The theory behind it presupposes a prior that a CDF that can take on uncountably many values. But in fact, whenever you're measuring something in the world, you know that the measurement process always leaves you with at most a finite number of values that are possible with your measuring instrument. And so we don't really have to achieve the goal, the theoretical goal of uncountably infinite, because that's not how the world works anyway. And the fact that this is hard, namely how to put a prior on your space of possible CDFs for your data, that's a hard thing to do. That task is not unique to Bayesians. It's equivalent to asking the question from a frequentist, ask where does your likelihood function come from when the frequentist has tried to fit probability models to observational data, and there's not any one and only one sampling distribution that comes naturally with the structure of the problem, which is almost always true with observational data. Then frequentists have to face this same issue, and they face it by not talking about putting a prior on all CDFs. They face it by a form of averaging across possible models that I'll be showing you later on. So what people often do in practice, like it says here at the top of the next page, is to appeal to considerations that narrow down the field. You might say to yourself, well, whatever's going on here, the distribution of the YI should be symmetric, for example. If I'm looking at a measurement process, there may well be no reason for positive large values to be any more likely than small values, and so that would suggest to restrict your attention to symmetric distributions. And then within the world of symmetric distributions, you try to find some relatively rich parametric family that's symmetric, and then hope that will be a substitute for all of the set of all possible CDFs. Strictly speaking, as I've said, you're not supposed to look at the data while specifying your prior on the set of all CDFs. That would be one of those using the data twice things that we talked about before, and would result in a failure to fully propagate the uncertainty about the model through to the things that you care about, leading, generally speaking, to narrower uncertainty bands than you should have. You should actually have wider uncertainty bands to account for the fact that you don't really know what the right sampling model is. But as I've just mentioned before, not doing so, not looking at the data as part of specifying your prior on model space, can permit the data to surprise you in ways that would make you want to go back and revise your prior. And the method I'm going to show you later on, called calibration cross-validation, is a Bayesian form of cross-validation that allows you to cheat, to look at the data to help specify the prior on model space, but then pay the right price for having cheated. It's a bit like the following analogy. Let's say you're trying to lose weight, and you are choosing between two things. One is to eat a nice piece of chocolate cake in front of you that has 500 calories in it, and the other thing to do is not. Well, okay, you're going to want to eat that chocolate cake, but if you do, then that will go against your goal of losing weight. And so there are actually two things you could do. One would be to not eat the chocolate cake, and the other one would be to eat the chocolate cake and then go right down to the gym and exercise off 500 calories. And it turns out that physiologists have shown that your body, one day from when you did that, will be at about the same place as if you hadn't eaten the chocolate cake at all. It takes about a day for the burn metabolism to catch up with the eating of the chocolate cake. But so you can get to approximately the same place one day later by either eating the chocolate cake and paying the price for it, so to speak, by going to the gym and working it off, or by not eating it at all. And the Bayesian calibration cross-validation approach is like the eating the cake and then paying the price. So we go ahead and we look at the data to see what the good models are, and then we go to the gym and work off the calories. And the equivalent analogy to that is we reserve some of the data just for calibration purposes, and that makes our inferential and predictive intervals wider than they otherwise would have been by an amount that's appropriate given how much uncertainty we have about the model. So I'll be telling you more about that later on. So we've got out-of-sample predictive validation, like I was talking about earlier this morning, and Bayesian nonparametrics as two things that we could use to try. Here's a new case study. This is our case study for continuous outcomes on the real line, and it will occupy us also when we start looking at better models for the data than our initial model. There used to be a part of the U.S. government called the National Bureau of Standards, NBS, and they're now called the National Institute of Standards and Technology, NIST. And for many decades now, they've been doing high-precision measurements of physical constants. And this might sound like rather boring work, but if you're going to try to create a system of weights and measures that describes the official weights and measures, then you have to be prepared to undertake the boring-sounding task of taking a little block of metal that's supposed to weigh some nominal weight and weighing it over and over again and looking at the nature of the measurement errors in your measurement process. The National Bureau of Standards people do this. This is a data set that was obtained back in the 1960s, early 1960s, in which 100 weighings, so our sample size here is 100, of a block of metal called NB10. The NB came from National Bureau, and the 10 came from the fact that it was supposed to weigh 10 grams. And they weighed this little block of metal 100 times under conditions that were as close to the independent, identically distributed theoretical goal as humanly possible. So each weighing was meant to be logically, physically independent of the other weighings, and the weighing process was done in such a way that the probabilistic behavior of what you might get on each particular weighing is as close to identical across the weighings as possible. And they got the following 100 observations, which are summarized here in a frequency chart. None of these numbers seem to have anything to do with 10 grams, so you have a right to wonder what I mean when I say that there was one 375 in a data set and one 392 and so on. But it turns out that already back in 1962, they were able to do weighings all the way down to 1/1,000,000th of a gram, a microgram. And so each of these numbers, it turns out that NB10 weighs slightly less than 10 grams by around 400 micrograms. And each of these numbers is coded as simply the number of micrograms below the nominal weight of 10 grams. So that's the story. And now the question is, how much does NB10 really weigh? And by that I mean, if they were to, in terms of populations and samples, these 100 numbers are a random sample from the population of what they would have gotten if they continued this IID weighing process forever. And so we're wondering what the mean is of all those measurements in the forever process. That corresponds to the so-called true weight of this block of metal. Secondly, they used to, before they started weighing it, they used to think that its true weight was some number below a value like 405.25. What do we think on the basis of these 100 weighings? What's our posterior probability that that's true? And thirdly, how accurately can you predict the next measurement? So if we wanted to try to understand their measuring process from a predictive point of view, how accurately could you do that? So those are going to be our three scientific questions. Now, to do this from the De Finetti approach, I should now put before even seeing the data, I should have put some kind of nonparametric prior on the set of possible CDFs for this data set and updated it based upon the data. Even that turns out to be harder than it sounds for reasons I'll show you later on. But I'm going to basically postpone the model uncertainty problem until later in the course because we need to know more than we know now to be able to tackle it fully. So for a while yet, I'm still going to pretend that it's okay to do the cheating thing, the looking at the data and seeing what's going on. So what you would probably do with this data set is you'd probably make a normal quantile plot and see how close the data values look to normality. And you might hope it's close enough to normality that you could model the data as the data gathering process is like draws from a normal distribution. So here's a normal QQ plot of the 100 measurements. They turned out to have a sample mean of 404.6 micrograms below 10 grams and a standard deviation, sample standard deviation of about 6.5 micrograms, below 10 grams. So here's the normal quantile plot. So you may recall the way these pictures are made. The vertical scale is the actual measurements themselves, sorted from smallest to largest. And the horizontal scale is numbers that are invented to stand for what the data should have looked like if it had followed the normal distribution. In fact, a kind of standardized version of the normal distribution, where you take away the mean from all the measurements and divide through by the standard deviation. And if you think about that, if you plot what the measurements are against what they should have been if they'd been normal, you ought to get a straight line if they are normal, right? That's the nature of the process. I don't know. It's actually quite hard to track down the history of who invented the quantile plot. But whoever did it was working off of the fact about human nature, that the nature of our eye-brain complex, that we do not discriminate very well differences between patterns that involve complicated shapes, two different patterns that involve complicated shapes. So you might have said, well, instead of drawing this picture, I could have just drawn a histogram of these numbers and superimposed the normal curve with the same mean and standard deviation on top of it. But it turns out that we humans are not very good at discriminating between two curves. We are much better at discriminating straight lines than we are at discriminating curves. And so that was the idea behind the normal QQ plot. You basically invent numbers that stand for what the data should have been if they were normal and plot them against the actual data values. And if they are normal, it'll look like a straight line. And that fits in nicely with the way the human brain can analyze things. Well, do we get a straight line? In fact, the straight line we should have gotten if things were normal is plotted on top of this normal QQ plot. So you can see that we don't have the same straight line as we would have had under normality. Instead, we do have something interesting. What's going on in the lower left-hand corner? An observation that's way too small, given what the normal curve expected. What's going on in the upper right-hand corner? Again, observations that are way too big. And so we have outliers in both tails. And in fact, this picture, believe it or not, is trying to tell us that the distribution is approximately symmetric. And the reason for that is as follows. If you imagine taking that and putting it on a piece of paper, and you fold, first of all, you fold this way so that the paper is now folded in half going along the vertical line at 0, and then you fold it again, you'll discover that the bottom half of this matches now the top half if you do that double folding. Can you kind of imagine that in your mind? Fold one way, then fold the other. Now the two halves match each other perfectly or almost perfectly. That's a way of saying that the distribution is symmetric. But now we can see that it actually has substantially heavier tails than the normal distribution does. And so a really good model for this data is going to involve a sampling distribution that is symmetric but with heavier tails than the normal distribution. Can anybody think of such a distribution? Cauchy is an example. Cauchy is a special case of the family I have in mind. What's Cauchy's special case of? The t distributions. And it's going to turn out that we're going to get a very satisfying model for this data by modeling the individual samples values as like draws from what later on we're going to call a scaled t distribution with unknown center and unknown shape, unknown spread, and also unknown shape in the form of not knowing what the right degrees of freedom is. That turns out to be a really good model for this data set. And in fact, that's no surprise to the people at the National Bureau of Standards. There was this very good statistician there for a long time named Churchill Eisenhart, who said that one of the things he wanted to have put on his gravestone was the measurement world looks a lot like t on 6 degrees of freedom. That was one of his little adages that he wanted to put on his gravestone. This data set's even more extreme. It's going to behave like t on 3 degrees of freedom, which is even farther away from normality than, of course, 6 degrees of freedom. But in order to fit that model, we need to sneak up on it by trying some simpler models first. And so I'm going to unrealistically pretend that this data follows the normal distribution first so we can get practice on fitting normal distributions to data. So one standard choice of an underlying symmetric distribution is the Gaussian. So here we have, if you knew what mu and sigma squared were, then yi would be IID normal with that mu and sigma squared. And then the mu and sigma squared have to have prior distribution. Now notice that this is already more complicated than all of our previous case studies, because if both mu and sigma squared are unknown, then theta, the thing that's unknown to you, is now a vector of length 2, whereas all of our previous examples, including in the homeworks, have all involved scalar unknowns, like a vector of length 1. So that aspect of it I'm going to postpone for a little while. First of all, equation 4 is, of course, the familiar normal density that we're going to need to work with, manipulate directly to work out likelihoods and things like that. Even though you can see from the previous graph that this is not a good model for this data, I'm going to go ahead and fit it anyway for practice in working with the normal distribution. Later on, we'll improve upon the Gaussian by fitting a t. The t distribution for people who are only frequentists would not ordinarily be thought of as a natural sampling distribution for data. It arose, as you may recall, as the repeated sampling distribution of some particular function of the mean and the standard deviation when you're trying to learn about the mean. That thing that Mr. Gossett, otherwise known as student, figured out in right about 100 years ago that gave rise to the student t distribution. But in the Bayesian story, it's quite natural to use any distribution that you can to see if you can get a decent model of the world, and we're going to use the t later on as the basis of our likelihood function. Now, this is more complicated than our previous models because, as I said a moment ago, the parameter here is actually a vector. And so I'm going to sneak up on the Gaussian even further by pretending that one of those parameters is known and trying to learn the other one. And so here it's more natural to pretend that sigma squared is known and try to learn about mu from the data because mu stands for the true weight of NB10, which answers question 1. On homework 3, you have an example, you have a chance to work through what happens in this model where we are going to pretend the other way around, pretend that mu is known and draw one-dimensional inference about sigma squared. So there's a problem about how to do that in the Gaussian family on homework, or problem set 3. Now, okay, so first we're going to consider a cut-down version of the model with 2 unknowns in which we pretend that sigma is known to be equal to its sample standard deviation value. Obviously, this underpropagates uncertainty because we're pretending we know something is truly equal to the value that we just got out of the sample, and the sample standard deviation is not a perfect zero variance estimate of the population standard deviation. Well, okay, then this simpler model has an easier form. If you knew what mu was, the yi's would be ID normal would mean mu and a known variance sigma 0 squared now. And then mu is like a draw. Your uncertainty about mu can be modeled as like a draw from a prior distribution on mu. So how do we build the likelihood function? You guys have seen the steps now. You take the marginal sampling distribution, which is this guy over here, equation 4, and you multiply together all of them across as I runs from 1 to n to get the joint sampling distribution, because that's the right story for the joint under the model for IID. And then you look at that function and think of it as a function of the unknown parameter given the data values. So the likelihood function in this model looks like this. It's what you get by multiplying all those marginal sampling distributions and now regarding it as a function of mu for fixed y. And also we're pretending that sigma 0 is known. Well, this is going to require some simplification. Let's take this constants and move them out of the product. In fact, we don't need them, right? Because since it's a likelihood function and arbitrary positive multiples are anything we want them to be, let's take the part called 1 over sigma 0 squared to 2 pi raised to the nth power, which is what you'd get by taking that constant out, and just call it c. And now the product of a bunch of exponentials is the exponential of their sum. And so this is equivalent to a constant times e to the stuff. And e to the stuff looks like e to the minus 1 over 2 sigma 0 squared times the sum as I runs from 1 to n of the squared discrepancies yi minus mu. Now, I want to look at that as a function of mu for fixed y. And I'd like to be able to figure out things like, well, what's a sufficient statistic in this model? And at the moment, it doesn't look good because at the way I've written it right now, it looks as though the likelihood function depends on the entire data vector for its evaluation. But we can do a little algebraic trick. Let's take that sum and expand it out. So I'm going to write it now as this thing here, where we've got the sum expands out to the sum of the yi squareds minus 2 mu times the sum of the y's plus n times mu squared, right? But now look, if I'm thinking of this as a function of mu for fixed y, the term inside the exponent called minus 1 over 2 sigma 0 squared sum of the y squareds doesn't depend on mu. And so it just gets absorbed into the constant. And so what's left, in fact, you can rearrange it to look like this. If you complete the square on bringing in the sample mean, I'm leaving out a few algebraic steps right here. But you can see right away by looking at the third line of equation 6 that a sufficient statistic for mu in this model is what? Having just argued that the sum of the y squareds disappears into the normalizing constant, what's left as the only function of the data that appears in the likelihood function? Just the sum of the y's, or equivalently the mean. And so no wonder in statistics 1 we tell people with normal data take the mean. And so that's because it's a sufficient statistic for the underlying population mean. And if I complete the square on mu using a little expansion around y bar, what turns out is a very nice formula, because you get the following expression: some constant times e to the minus 1 over 2 times stuff times mu minus y bar squared. Well, look, that looks like a normal curve. That's actually a normal curve in mu, centered at y bar, and having a variance given by sigma 0 squared over n. Because if you think about how the standard formula for the normal works, that's exactly what's going on. So the likelihood function, when thought of as a density for mu, is a normal distribution with mean y bar and standard deviation sigma 0 over the square root of n. And those numbers are kind of meaningful, right? Because if we were being frequentist about this, we would use y bar as a guess for mu, and the frequentist standard error we would use for y bar is exactly sigma 0 over the square root of n. So we're getting another one of those things where the Bayesian and the frequency stories agree with each other, and this is Bernstein-von Mises again showing up in that way, that you get the same answer when you have a lot of data. So I've just said that. Now, that's the likelihood function. If we were to find a conjugate prior, we have to go through the usual two-step process. We have to say, well, the likelihood function came out a normal distribution in mu. Is there some other family? Well, let's see. You don't even have to look any farther. Look back at our previous two case studies. We looked at the form of the likelihood function in the Bernoulli, and we saw it looked like a beta. And so we said, well, maybe the prior could be taken as a beta, and the product of two betas is another beta. Boom, we got it. In the Poisson case study, we looked at the likelihood function as a function of lambda, the parameter, and we saw it looked like a gamma distribution, and the product of two gammas is another gamma. So maybe the normal is going to turn out to be the conjugate prior in this model. That would only be true if the product of two normal distributions is another normal distribution. So let's find out. So we've also noticed that y bar is a sufficient statistic. It turns out also to be a minimal sufficient statistic. So in finding the conjugate prior for mu, it would sure be nice if the product of two normal distributions is another one, because that would show conjugacy. So suppose, just to see where it leads, therefore, that the prior for mu is taken to be normal with mean mu 0 and variance sigma squared mu. Then you just write out Bayes' theorem. The posterior is the prior times the likelihood, and so there's the prior and there's the likelihood, and you want to bang them together and simplify. So that's the resulting expression, and we want that to be, we want it to be a normal curve in mu. So we want it to be of this form here: a constant times e to the minus a half times some number a times mu minus b quantity squared plus c. If we can write it that way, that's going to correspond exactly to the normal family, where I have to identify A and B and C in terms of what I actually have there. And that's, yes, please. You don't actually, but in fact, if you're starting out with any quadratic function of mu, you can write it in the form A times mu minus B squared plus C. That will capture any quadratic function in mu. So I can see that the second line of equation, rather the third line of equation 7, is going to come out as some kind of quadratic function of mu. And I'm hoping that I can express it as the right kind of quadratic function of mu. And so, as you're saying, C is about to drop out completely. But whatever these things are, B and C can be whatever they want, but A has to be positive, because you remember the Gaussian has to go over the form e to the minus 1 over 2 times something. In other words, the stuff outside of the mu minus something squared has to be negative. So we have to have a positive number for A, and B and C can be whatever they want. Well, Maple actually can help with this. It has a command in it, a function called collect, and so I give it that particular function that's in the exponent in the last line of equation 7. I give that as the argument to the collect function, and I say, please collect all like terms with respect to the variable mu, And what it does is it expands out mu into a quadratic, and it collects all the mu squared terms together, and it collects all the mu terms together, and it collects all the constant terms together. So that's nice and cool, and everything is there in nice symbolic form. And now, if I match coefficients, as this gentleman has pointed out, we don't care about C, it just disappears into the normalizing constant. But if we match coefficients for A and B, we find a very cool thing. It works. A has to have the form 1 over sigma mu squared plus n over sigma 0 squared. In fact, look at it right there. It's right there in front of us. The maple statement at the bottom of page 6. There it is right in front of us. And B has to have a slightly more complicated form that's based on the way B was going to work. B was going to be the number that made A times mu minus B squared work. And so when you solve for that and hold your breath a little bit and get the algebra right, B has a very interesting expression. But all we needed was a value of B that works and a positive value of A that works. And you can see that everything in the expression for A is positive. We're all adding together positive numbers. So since A is greater than 0, this has demonstrated two things. First of all, the conjugate prior for mu in the model where the sampling distribution is normal with unknown mean and known variance is another normal curve. And secondly, the conjugate updating rule is very interesting because A turns out to be the posterior variance, and B turns out to be the posterior mean in this posterior normal distribution. So check it out. If your model for the data is that if you knew what mu was, the yi's would be conditionally IID normal, given mu would be IID normal with mean mu and some known variance sigma 0 squared. And if your uncertainty about mu is well captured by thinking of it as like a draw from a normal distribution with mean mu 0 and sigma variance sigma squared mu, and we have n observations, then the posterior is another member of the normal family. And the prior to posterior updating rules are interesting. The prior mean mu 0 updates to the mean mu star, which corresponds to the number B that I had above. And it has that particular form, which I'm going to talk about in a minute. And the posterior variance is actually not A, as I said a moment ago by mistake, but 1 over A. So the posterior variance is 1 over that expression right there. But look what the posterior mean is trying to be. What have we seen all along in all of our conjugate examples? The posterior mean has been a weighted average of the prior mean and the data mean with weights given by something that was driven by the prior sample size and the data sample size. And look, that's what that expression for mu star is trying to say. Because we have mu 0 as the prior mean getting weight 1 over sigma mu squared, and we have the data mean y bar getting weight n over sigma 0 squared, over sigma 0 squared. And then the denominator is just the sum of those two weights. So it is literally a weighted average of the prior mean and the data mean. We have not yet quite set things up so that the weights correspond to the prior and data sample sizes, because the thing in front of y bar still has a sigma 0 squared in it. But I can readily fix that by multiplying the numerator and the denominator by sigma 0 squared, and that'll isolate the n by itself in front of the y bar, which is what I want. So now we're starting to see things that look like 1 over variances, right? Because we found that the likelihood had a prior variance, rather the likelihood had a variance of sigma squared 0 over n, or sigma 0 squared over n. And look, that form n over sigma 0 squared seems to be coming up in this updating rule several times. And so we're starting to see that something that is driven by the reciprocal of the variance of a distribution comes up quite naturally in Gaussian modeling. And since it comes up often enough, Bayesians have given it a name. They've called it the precision of a distribution. It's just for any distribution you're thinking of, calculate the variance and take its reciprocal. We're going to agree to call that the precision of that particular distribution. And in fact, it's a sort of a happier way to think about uncertainty, right? Because sigma squared represents how much you don't know. It represents uncertainty, whereas 1 over sigma squared represents how much you do know. It's essentially, it comes out on the information scale rather than on the how much information you don't have scale. There's that old thing about the glass of water being half empty or half full. The precision way thinks of as half full, and the variance way thinks and the standard deviation ways think of it as half empty. So look what's happening. The posterior mean is a weighted average of the prior mean and the data mean, where the weights are given by the precisions. There's a thing called data precision, and that's just the variance of the likelihood function back here, which we saw was sigma 0 squared over n. Take the reciprocal of that, you get the weight n over sigma 0 squared. So there you go. And evidently the prior mean is getting a weight equal to the prior precision, but that's also correct, because remember what our prior was? Our prior was normal with a variance of sigma mu squared, and so the prior precision is just 1 over sigma mu squared. So very cool. And what's happening over here in the variance is also interesting. Look what it says. If I took the reciprocal of both of those equations on the right part of 11, I would get the posterior precision, 1 over sigma squared star, is equal to 1 over sigma mu squared plus n over sigma 0 squared. In other words, what it's trying to say is that on the precision scale, information is additive. The posterior precision equals the prior precision plus the data precision. So with this convention of what precision means, the equations in 10 and 11 have a series of nice intuitive interpretations, and here they are. I've already said most of them, but here they are again. The prior, considered as an information source, is Gaussian with mean mu 0, variance sigma squared mu, and precision therefore 1 over sigma squared mu. And when viewed as a data set, consists of n0 observations, the prior sample size, which I have not yet determined. Secondly, the likelihood, when considered as an information source, is Gaussian with mean y bar, and variance sigma 0 squared over n, and therefore precision n over sigma 0 squared. And when viewed as a data set, consists of n observations, obviously, because that's how big the data set is. Third thing, the posterior, considered as an information source, is also Gaussian, and the posterior mean is a weighted average of the prior mean and the data mean, with weights given by the prior precision and the data precision. So that's quite cool. On the precision scale, you get the weights out that stand for how much weight you should give to the prior information and the data information in the posterior weighted average. And moreover, the posterior precision, which is the reciprocal of the posterior variance, is just the sum of the prior and data precisions, which is why Bayesians invented the idea of precision in the first place. On this particular scale, information about mu is additive. Posterior precision equals prior precision plus data precision. And now finally, rewriting mu star, that's the form it has now. Let's multiply everything through by sigma 0 squared to get the n by itself next to y bar. You can see right away that the prior sample size is whatever comes out sitting next to mu 0 in that final expression in line 12. And so the prior sample size in this model is just sigma 0 squared over sigma mu squared. And that makes a lot of sense. The bigger sigma mu is in relation to sigma 0, the less prior information is being incorporated, and that makes a smaller prior sample size. So that's a nice way to understand how updating is working. It's a normal model where we pretend we know the right variance, and we try to learn about the mean. And this beautiful thing happens where the posterior is also Gaussian with a conjugate Gaussian prior, and the posterior mean turns out to be a lovely weighted average of the prior mean and the data mean, where the weights are given by the precisions. And on the precision scale, the information is additive. Posterior precision equals data precision plus prior precision. Now let's try to be more realistic and allow both mu and sigma squared to be unknown. So now this model has a two-dimensional parameter vector, k equals 2 unknowns in it. And let's see if we can figure out what's going on. This is our first time, and all the rest of the course practically pretty soon, all of our problems will be multi-parameter. Let's see what's going on. Do we have to have a new version of Bayes' theorem to account for vector unknowns? Well, let's find out. Let's try to write down the old one and see if it adapts naturally. So let's just write it down and see what it looks like. If it were to work, the left-hand side of equation 14 would say the posterior distribution for theta, which is now a vector given y, which is also a vector, of course. All along, y has been a vector of length n. But the posterior distribution for theta, which is a vector of length 2, would be equal to that stuff on the right. Is there anything wrong with that symbol on the left? Is it perfectly reasonable to talk about distributions that are bivariate distributions? Well, sure. So the left-hand side of this is simply a bivariate distribution where it has two components, mu and sigma squared, and both of them are unknown. And so That's like it says in the second part of the top line in equation 14. P of theta given y is just P of mu and sigma squared given y together. It's a kind of a joint posterior distribution for both unknowns given the data. Well, let's try writing down the Bayes' theorem and see if it works. That's supposed to be equal to a constant, a scalar constant times the prior distribution times the likelihood distribution. But look, P of theta is just a bivariate prior, namely P of mu and sigma squared. And the likelihood function is just a bivariate likelihood density, namely L of mu and sigma squared given y. And when you evaluate a multivariate density at a particular point, you get a single number. And so P of mu comma sigma squared times L of mu comma sigma squared given y is just going to be a number. And that matches the dimensionality of the left-hand side, because when you evaluate P of theta given y at a particular theta, you just get a number again. So interestingly and very, very nicely, what happens with Bayes' theorem when you try to apply it to a vector of unknowns is that you don't need to do anything new. It's the same theorem. It's just you have to remember that the thing that's unknown is a vector now, rather than just being a single number. Later on, the same theorem applies when theta turns out to be not just a vector, but a matrix. Later on from that, it turns out to be the same theorem when theta turns out to be a function, like a cumulative distribution function. Bayes' theorem works when you stick anything into it, basically. And it's just that it becomes a probability density on this new space of possible outcomes as a product of two other probability distributions on that space of same outcomes. So nothing new. However, if you were to try to actually implement this by writing down a particular prior and a particular likelihood, to find out what the posterior is, you would have to work out that normalizing constant C in there. And when K is of dimension, when K, the number of components, is bigger than 1, it's going to have to be a multiple integral now. In this problem here, where K is 2, it's a bivariate integral. For instance, here, C is just 1 over P of y, which is 1 over the double integral of P of mu and sigma squared and y d mu d sigma squared. So you have to make a double integral over the joint distribution of all three of those things. And it can also be written as the double integral over the prior times the likelihood. Now you can also see that if K, instead of being 2, was 50 or 100, then evaluating the normalizing constant is going to be a real pain in the butt. It's going to be a 50 or 100 dimensional integral to evaluate. So already we're beginning to see that one of the big implementational difficulties of the Bayesian paradigm is it forces us to think about high dimensional integrals. And not just think about them, it forces us to evaluate them. Okay, worse is in store, or at least more of the same is in store. We've now seen that you have one k-dimensional integral you have to be able to approximate in order to work out the normalizing constant. Later on, when we use the T model, for instance, on the NB10 data, we're going to have a vector model to think about. Where the joint posterior distribution is going to be over mu and sigma and nu, given the data and the background information, of course. So these three components are what the theta vector is going to be. And we are eventually going to be able to use Bayes' theorem to work out what that posterior distribution is. But we can't, as humans, we can't even plot that distribution. Because to plot it, we would need four-dimensional coordinates to plot it. We'd have to have a direction for mu, a direction for sigma, a direction for nu, and a direction for the height of the density. You could just barely get a sense of it in 4 dimensions by doing a kind of 3-dimensional color plot, I guess, right? You could have a dimension for mu and one for sigma and one for nu, and then you could plot points in which the color of the point was driven by the height of the density there. The bigger the number, the redder it became, for example, the smaller the number, the bluer it became, or something like that. So we could just barely visualize this thing here. But if K had been any bigger than 3, we'd be in trouble. We can't even make a fairly complicated visualization of it. So how do people go about visualizing high-dimensional probability distributions? One of the most natural things is so I'm going to just remind us that this is hard to visualize. when k is bigger than 1 even. And so what people tend to do is they start thinking about, well, let's talk about the marginal posterior distribution for mu. And we'll just look at that dimension of it. You remember that old story about the blind men who are trying to figure out what animal it is, and one of them is holding onto the trunk, and one of them is holding onto the leg, and the other one's holding onto the tail, and so on. We can try to get some sense of this three-dimensional posterior by looking at its one-dimensional features. So I would want to think about what's the marginal posterior for mu given y in the background. And you know from the law of total probability that the way you would compute that is you would write down the joint posterior for both mu and sigma and nu given the data and the background, and you would integrate over sigma and you would integrate over nu. So in this problem here where k is 3, to get the marginal for mu, you have to perform a k minus 1 dimensional integration. And if you wanted the other marginals, you'd have to have other additional k minus 1 dimensional integrations. And so in general, when your unknown is a vector of k components, you have to do one numerical integration, one numerical or symbolic integration in k dimensions to get the normalizing constant. You have to do k integrations, each of dimension k minus 1 to get all the marginal distributions. Going farther, so this next part just talks about the marginals. So in this little model here where we just had 2 of them, it's like what I just wrote down. Oops, I'm over here now, sorry. It's like what I wrote down a minute ago, except all I have to do is marginalize over sigma squared. So people refer that process as integrating out the nuisance parameters. So here, if mu is the main parameter of interest, and then we write down the joint posterior and integrate over the nuisance parameter to get the marginal posterior for mu, or people just call it marginalizing over sigma squared, for instance. And predictive distributions also involve a k-dimensional integration, because you may remember from the way our logic of how we construct predictive distributions, we have to take an integral over all the components of theta, and it'll be an integral of the product, that mixture of the sampling distribution weighted by the posterior. So we get a k-dimensional integral to evaluate the normalizing constant, k separate k minus 1 dimensional integrals to get the marginal posteriors, and another k-dimensional integral to get the predictive distribution for future data. And finally, if you're interested in some function of the parameters, there's additional difficult integrations ahead of you. And I won't dwell on this too much because people hardly ever do this, and it's much easier to do with Markov chain Monte Carlo. But suppose you wanted the posterior distribution for some function, one-dimensional function of the parameters in the Gaussian model, namely the coefficient of variation, which is given by the standard deviation divided by the mean. It's a way to measure how noisy the distribution is relative to the signal that is actually present in the distribution. Well, that's a function from 2 dimensions, g1, from 2 dimensions down to 1. And the way you'd have to do it if you were going to do it in closed form is you'd have to come up with a second function of the parameters. Say the previous one was called lambda as the one-dimensional coefficient of variation. You'd have to invent some new parameter eta, which was another 2-dimensional function of mu and sigma squared, mapping from 2 dimensions down to 1, such that that mapping from consisting of g1 and g2 from the original parameterization mu and sigma squared to the new parameterization lambda eta is invertible. Then you'd have to compute the joint posterior for lambda and eta through this thing that people call the change of variables formula, which requires evaluating the determinant of the Jacobian of the inverse transformation. And this is all, if this is all gobbledygook to you, don't worry, because we're not going to do this stuff. And then finally, once you did that, you'd finally have to marginalize in lambda by integrating out eta. So there's all this stuff to do. And what you'd have to do in the end, after all you did all that stuff, is you'd have to work out one more k minus 1 dimensional integral to get what you want. So actually, there's 2 integrations here. One of dimension k to get the normalizing constant in that density 18, and then another one of dimension k minus 1 to marginalize and get rid of the eta. So tremendous pain in the butt here. We're in real trouble. When k is a lot bigger than 2, all these integrals may create severe computational problems. And this was well known. It was hinted at in Mr. Bayes' own life by him saying in this mumbling sort of way in his manuscript that this looks hard to me when I start thinking about problems that are more complicated than my Bernoulli problem. He was thinking about a Bernoulli problem just like we did in the first case study. And Laplace understood 20 or 30 years later that this was definitely a possible barrier to implementation, and that's why he invented those Laplace approximations. And so he did a lot of numerical integration, approximate numerical integration in his life, just by using, Laplace approximations are just a particular way of doing Taylor series. So he used Taylor series to get nice analytic approximations that could be evaluated numerically. That's how he solved the integral problem. And then when he died, as I mentioned to you, his method was forgotten. So we will talk a little bit about Laplace approximations in the unit about model comparison, because it turns out that they are key to one particular method you may have heard of before for comparing one model with another that's called the Bayesian information criterion, BIC. That turns out to be, you can understand it by thinking about Laplace approximations. But these days, people mostly use one variant or another of an entirely new idea, which was not feasible in Laplace's time and was not feasible in Fisher's time, and only really became feasible for us peons who don't have access to supercomputer mainframes around the year 1990, really. Somewhere around 1985 or 1990, desktop computers, the kind of machines you could buy for your own office and run, became fast enough and had enough memory that methods based upon simulating from the Pasteur distribution were such that you could get an okay answer if you ran your desktop computer overnight, for example. About 8 hours of computing with a 1988 level computer was good enough with this method. And so finally Bayesians had a way in the late 1980s and onward, this method called Markov chain Monte Carlo, to learn about even quite high dimensional Pasteur distributions. The idea is wonderful, and it was first noticed in considerable detail by Mr. Gossett, the guy for whom the student T distribution is named. Mr. Gossett, I don't think I've talked about him in here. Have I said anything about him? He was a statistician. In fact, he was the only statistician working for the Guinness Brewery Company in Dublin. And they had a series of quality control problems to solve. They wanted to vary the basic Guinness formula. If you've ever made your own beer, you know there aren't that many ingredients you can vary. You have water and yeast and hops and something that has sugar in it. That's basically it. That's how you make beer. And the something that has sugar in it is usually what you get by taking a grain like barley and roasting it to bring out the sugars, and then grinding up the roasted barley and boiling it in water. And the resulting syrup is called wort, W-O-R-T, and consists largely of sugars that have been freed by the boiling process from, and they were created by the roasting process, and then they're freed by the boiling process. As you know, alcohol is produced as a byproduct of yeast. They eat the alcohol and secrete, they eat the sugar and secrete the alcohol. And so that's it, water and hops and barley and yeast. You can vary those four things. But Guinness is most famous, of course, for its stout beverage, which is a very dark beverage. And the way they get the darkness is they roast the barley for a very long time until it blackens, and that black color shows up in the drink itself. But you could change what kind of barley you're using, and you could change the concentration of barley per barrel of beer, and you could change which hops you're using, and you could change which yeast you're using. They never thought of changing the water. In those days, in the very early days of Guinness production, they just took the water right out of the Liffey River in Dublin, and they did a little bit of purifying on it, but they more or less hoped it was pure enough, and and then the process of boiling the water in the wort was going to kill off anything that was going to be bad for you, and that was how they made the beer. So essentially, they wanted to do a quality control sort of problem in which they varied the ingredients and came out with different versions of Guinness Stout, and they wanted people to drink these different versions and try them. So they brought people in and said, here, we're going to give you 5 different versions of Guinness Stout. Have a little sip of each one and tell us which one you like best. And the reason that number's 5 and not 40 is that, as you know, when you're tasting things, after about the 3rd or 4th thing you've tasted, you start having trouble remembering what the first one tasted like. Especially true with alcoholic products, I might add. And so Mr. Guinness, Mr. Gossett was always forced to work with small sample problems, and because he was forced to have small numbers of observations per person, and that forced him to develop the T machinery that people use now as an as a correct way to deal with the situation where you have a small sample size and unknown mean and also unknown variance. And I see it's time for our first break, so I'll finish this story after the break. We'll start again at 2:45. Video guys, we're going to start again now for the next hour from 2:45 to 3:45. I was telling you some history about Mr. Gossett and why he was the first guy to have invented what we now call Monte Carlo methods. Here on this page of handwritten notes, his problem was as follows. His outcome variable, he could model it reasonably as approximately normal, but he didn't know either the mean or the variance, and his problem was that his sample size, little n, was small, on the order of 5. And the best practice when he was working, before he did his work on what we now call the T machinery, best practice was to pretend that the repeated sampling distribution of y bar minus mu over s over the square root of n, where y bar is the sample mean and s squared is the sample variance, the usual unbiased sample variance. People pretended that that followed the normal distribution, the standard normal distribution with mean 0 and standard deviation 1. And then they went ahead and did inference based on that. And he was a guy who's had a very acute something for nothing bell in his head. That's what part of what made him such a good scientist. And he said that can't be right when n is small because I used the data in 2 places in this expression. And I have to account not only for my repeated sampling uncertainty of y bar, but also my repeated sampling uncertainty of s. And so he actually answered this question with the world's first really serious simulation experiment. In 1908, with no computers, he did the following. He generated pseudo-random numbers from a normal distribution with known quantities for the mean and the variance. And there were already pseudo-normal tables available. Somebody had done that for him. So he just got together this little army of clerical workers at the Guinness Brewery and paid them overtime to do this at nights and on weekends. And they wrote down pseudo-random normal values on scraps of paper, and they put them in haphazard ways into things like shoeboxes and hats. And he had these people, for a period of many, many hours, pulling numbers at random out of the hat and grinding through, making little pseudo data sets, normal data sets, and grinding through the empirical distribution of y bar minus mu over s over the square root of n. So he had people doing what computers do for us now. And I don't know whether you know this, but I was a grad student at Berkeley from 1976 to 81. And even in those days, when Mr. Neyman was still alive and no longer running the department, but still alive, there was a job category at UC Berkeley called computer, and it was a person, not a machine. And Mr. Neyman still employed a woman whose job title was computer. And so essentially what Mr. Gossett did in 1908 was he turned the clerical people into computers. And they repeatedly simulated from the normal distribution. And actually, he developed the empirical distribution of this particular ratio and then went and looked. Carl Pearson had previously published a bunch of papers on what were called the Pearson families of distributions. And he went around and looked to see was there a Pearson family that matched the empirical distribution he found. And he found that there was one. And he published a paper in which he said, I can't prove this for sure, but my empirical work shows that I think this distribution follows what we now call the T distribution on n-1 degrees of freedom. And so he proved that result using simulation methods in 1908. The next time anybody did something serious with simulation was many decades later, that I'm aware of anyway, was around the year 1942. And the heroes of this story are a guy called Nick Metropolis, who was an American applied mathematician. And the guy he worked with on the first paper of this kind was a Polish mathematician named Stanislaw Ulam, Stan for short. What Metropolis and Ulam noticed, and this is going to be the basis of our work on MCMC starting next week, is the following quite profound fact, which was an interesting thing to notice in 1942, because even if you noticed it was true, you couldn't do anything about it yet because there weren't any computers. Here was the fact that they noticed. Anything you want to know about a probability distribution of arbitrary dimension, as long as that dimension is finite, anything you want to know about that distribution, you can learn by developing a method to simulate random draws from that distribution. actually quite a deep result, because it means that we don't have to work with analytic forms for complicated probability densities anymore. If we can just figure out how to simulate random draws from them, then anything we want to know about them can be found by simulating enough random draws from such distributions. And that's going to turn out to be the way we're going to solve the Bayesian computational problem. We're going to approximate these integrals without even thinking that what we're doing is approximating the integrals. It can be very cool. You'll see how it turns out. You probably know some methods for doing approximate numerical integration from your early calculus classes if you thought back and sort of dusted off the ideas, involving things like trapezoidal method and Simpson's method and so on. This method is completely different from that, and it's going to end up doing the integrations for us in this very cool way that doesn't even look like we're integrating anything. Very cool. So that's going to start next time. Maybe by the end of the day if we push through. All right, so let's go back to the model in which both of the mu and the sigma squared are both unknown. Oh, sorry. Yes, thank you. Sorry. I always forget that. It does turn out in the model where our model is now that the data are IID normal, mu, sigma squared, where both mu and sigma squared are unknown. It does turn out that there is a conjugate prior in this model. As the dimensionality of the parameter vector increases, it becomes harder and harder to find a conjugate prior. But for this model, there is a conjugate prior. And the simplest way to describe it is hierarchically. And this is that same idea I showed you before. If you want to model a bivariate quantity, mu and sigma squared, jointly, one way to do that is to first model sigma squared and then model mu conditional on the sigma squared you got before. And so I can describe the prior to you either by telling you what its joint behavior is or by telling you about its hierarchical behavior. And you could either start with sigma squared and then talk about mu given sigma squared, or the other way around. And it is vastly more natural to, it turns out, start with sigma squared and then talk about mu given sigma squared. So the sigma squared layer of this hierarchical prior that's conjugate turns out to be a draw from a distribution you've never seen before. SI stands for scaled inverse, and so that first line of equation 19 says sigma squared is like a draw from a scaled inverse chi-square distribution with parameters nu 0 and sigma 0 squared. And the reason that it's an inverse is that actually we're taking the idea of drawing a chi-square value and then taking its reciprocal. That's the idea of inverse here, inverse like reciprocal. So saying that sigma squared is like a draw from that particular scaled inverse chi-square distribution is like saying that 1 over sigma squared, the precision, follows a scaled chi-square distribution. And the scaling is chosen in a clever way so that sigma 0 squared can be interpreted as a prior estimate of the thing we're wondering about, sigma squared, and nu 0 can play the role of the prior sample size. So basically, when you write down that prior, you should think of a prior data set with nu 0 observations and sample standard deviation sigma 0. That's how you think about how to specify those numbers. Now, you may recall that the chi-square distribution is a special case of the gamma distribution. And so scaled inverse chi-square must be a special case of what people call the inverse gamma family. And the way you get an inverse gamma random thing is you just make a draw from a gamma and then take its reciprocal. So inverse gamma is just 1 over gamma. And the density of the inverse gamma family, actually the density of the scaled inverse chi-square family is this ugly expression here on the second line of equation 20. And you can get that directly from that appendix that I've given you copies of on the course webpage. So nasty looking distribution. And you can verify with Maple or read it in a book that this distribution has mean given by the expression you see there in equation 21 and variance given by that other expression. But these means and variances only exist if the prior sample size is at least 2 in the case of the mean and at least 4 in the case of the variance. Having made a draw from sigma squared, for sigma squared from that scaled inverse chi-squared, the way you simulate from the prior is you make a draw from a normal distribution conditional on the sigma squared you got a minute ago. And the parameters of the normal are mu 0 and sigma squared over kappa 0. And that form, I hope, would be quite suggestive to you because it acts like sigma squared over n. And that suggests that what's going on in this normal is that mu 0 acts like the prior estimate of mu, and kappa 0 acts like the prior sample size, in the same way that we would think of a variance over a sample size being the variance of the sample mean. So there we go. And now you can write out the likelihood function with both mu and sigma squared unknown. And we start with the same expression we had before, but now both mu and sigma squared are unknown. And you shove it around by expanding out the square in the yi minus mu squared thing. And you mess about with that a little bit. You introduce a y bar and poke around a little bit more. And what turns out to be true is that the likelihood function can be expressed as c times sigma squared to the minus a half n times e to the stuff. And e to the stuff looks like that second line in equation 23, namely minus 1 over 2 sigma squared times the sum of two things, n times mu minus y bar squared plus n minus 1 s squared, where s squared is the sample variance. So there's our likelihood function. And you can see by inspection that, fortunately for us, what we've been teaching everybody in statistics 1 for all these decades is right. If your data is Gaussian, then the sample mean and the sample variance are good things to use to summarize it. In other words, y bar and s squared are sufficient, are jointly sufficient. So the sufficient statistic is a vector of length 2 in this problem, and y bar and s squared together are jointly sufficient for mu and sigma squared. All right, well, what does this likelihood function look like? It's actually only three-dimensional, right? I could plot mu in one direction and sigma squared in another direction, and then the height of the likelihood in a third direction. And that's just 3D plotting, and Maple knows how to do that. And so I've done that here. I define a function called L, which is a mapping from mu and sigma squared and y bar and s squared and n to the thing we just saw. And I said, okay, that's my L, and now let me go ahead and use the plot 3D command. And it looks like the following cool thing. So the likelihood function in this problem, using the data values from the NB10 data set, it looks sort of like what you'd get by taking a rug on the floor that was a loose rug and grabbing it at some point and then just pulling straight upwards. It sort of looks like a mountain. And you might think that it was a symmetric mountain, but actually it only turns out to be symmetric in one direction. It's symmetric in the mu direction, which you can kind of see looking at this picture, and it's asymmetric in the sigma squared direction, which you can also kind of see looking in this picture. But you can see it more directly by the following. You can use the mouse to rotate 3D plots and get other useful views of them. So I'm actually going to rotate to where all I see is a kind of projection of this thing, or shadow plot onto the mu dimension. And I'll do the same thing for sigma squared. And so here's a shadow plot of this likelihood function in the focusing only on the mu direction. And it's symmetric, and it looks a lot like either a normal distribution or maybe a t-distribution. Turns out to be actually a scaled t-distribution. And the shadow plot for the sigma squared part looks just like what you'd expect. Since it's a measure of uncertainty about scale, and it can't go below 0, it's probably going to have a long right-hand tail, and it does. So there you go. And so it looks a lot like a gamma, or actually maybe an inverse gamma. It turns out it's actually an inverse gamma distribution. And I can make a contour plot of the same likelihood function. And here, Maple has done that for me. And what you see, these are the level sets. So it's plotting all the points that have the same likelihood value as that likelihood value varies from big to small. The biggest likelihood numbers are in the middle, and the smallest ones are further away. And this looks a lot like a joint distribution of two uncertain quantities that have what particular property in common, as to how they relate to each other. If you thought of this as like a scatter plot, where there were points falling in the scatter plot that followed contours like that when you summarize them, what's the main thing you see in how mu and sigma squared are related? What's their correlation? You know what bivariate normal scatter plots look like. When the plot is completely parallel to the x and y axes, the two variables in question have correlation what? Correlation 0. And so in this model, mu and sigma squared are uncorrelated with each other as uncertain quantities in the likelihood function, and that makes good sense actually. If you think back to what you may have learned earlier in the frequentist world, y bar and s squared are uncorrelated with each other in the Gaussian sampling distribution. So you can see that, and you can also see the symmetry of mu by projecting the contours down onto the mu axis. And you can also see the asymmetry of sigma squared by projecting the contours over mentally onto the sigma squared axis and seeing that they go farther out into the big numbers than they do down into the small ones. Okay, now it turns out that something good happens, and I'll spare you the details. Having adopted that conjugate prior, if in fact whatever prior information you have is quantifiable through this conjugate prior, what of course we would like next is simple expressions for the marginal posterior distributions of each of the parameters, and then also for the predictive distribution for the next observation. So, fortunately, in this model, all of the integrations can be done analytically, and Bernardo and Smith show how things come out, and we get the following results. We have a certain kind of conjugacy happening for sigma squared. Sigma squared started out as a scaled inverse chi-square in the prior, and it's also another member of the scaled inverse chi-square in the posterior. The marginal for mu, if I had known what sigma squared was, the conditional posterior for mu given sigma squared would have been another normal distribution. That would have been another kind of conditional conjugate updating. But if you integrate over sigma squared and just get the marginal for mu, it turns out to be a member of the scaled t distribution family, matching what the frequentists get when they look at Mr. Gossett's ratio. And the predictive distribution for the next observation is another t distribution. Here, the script g in the part that says things like sigma squared given y and script g is in there. I'm emphasizing that we're conditioning on the Gaussian assumption for our sampling distribution. Now, each of those expressions in equation 24 involves things I haven't defined for you yet, like nu suban and sigma squared suban and mu suban and kappa suban. So they're all defined down here at the top of the next page. And in fact, the updating rules are simple and quite pretty. I said that nu zero was the number of prior votes you could think of in the prior for sigma squared, and nu n is just equal to nu zero plus n. So basically, it's the usual thing where the posterior information is equal to is driven by the prior sample size plus the data sample size. The same thing is true for kappa n. It's equal to kappa 0 plus n. The posterior mean, mu n, has a nice interpretation. Check it out. It's a weighted average of the prior mean and the data mean, weighted by the prior sample size and the data sample size. So the same thing happens here as we've seen before. And the posterior variance is quite an interesting quantity. It has three components in it. The first one is driven by how much uncertainty you have about mu. How much uncertainty you have. The information that you have about sigma in the prior, that's that number sigma 0 squared. The second term is driven by how variable the data are. And the third term, very interestingly, is driven by how discrepant the sample mean is from the prior mean. And so, in other words, it's actually possible in this model for discrepancies between the prior and the data to show up as more uncertainty than you had before you started. You can start out with a particular prior distribution on these parameters and end up with a posterior that is more spread out than the prior. And that's because there could be a violent conflict between the data and the prior. And that's exactly what you would want to happen in Bayesian reasoning, right? If the prior and the data are supposed to bring information together, but if there's a violent conflict between the prior information and the data information, you would like the posterior to reflect that violent conflict by actually having more uncertainty in it than either information source did by itself. And in this T model with, or rather this Gaussian model with both parameters unknown, that's exactly what can happen. All right, now each of these things can be, I need to tell you what the scaled T distribution is. It's just, we take the ordinary T distribution from the back that's been tabled in the back of statistics books or is available in the R package, and we simply scale it with respect to location and scale. We shift it and so on. So a draw, W is like a draw from a T distribution on new degrees of freedom with parameters mu and sigma squared. That's equivalent to saying that W minus mu over sigma is a draw from the standard T distribution we know about from frequentist analyses, the T distribution with new degrees of freedom. And so this turns out to have a density expression given by the one here. And this distribution has mean mu as long as the degrees of freedom are bigger than 1. And variance nu over nu minus 2 times sigma squared as long as the degrees of freedom parameter is bigger than 2. So once again, we see that what's happening is we've got a weighted average of the prior mean and the data mean with the weights given by the prior sample size and the data sample size. And now we can use this Gaussian model, which I remind you is still not a very good model for the data because the real data values have outliers in both tails. But we can now use the Gaussian distribution with both parameters unknown to answer those three questions I started with at the beginning. So, what, if anything, did you know about the weight of this block of metal NB10 before I showed you the data set? The answer is you knew very little about it. And that was the same information base that I had before I started analyzing this data also. I would have thought that it would have had a value around 10 grams, because it's supposed to weigh 10 grams. But if you told me that they were measuring things down to the level of micrograms and deviations from 10 grams on the microgram scale, I wouldn't know anything at all very much. I might center my prior at 0 on the micrograms below 10 grams scale, but then have it have a very wide degree of variability in it. Similarly, I know absolutely nothing before looking at the data about the accuracy of the NB10 measuring process. So I'd like to put down a diffuse prior in this world as well. And that means I have to look at the nature of the meaning of these prior inputs and see what they mean. So let's go back and look at this again. Oh, actually, that's the likelihood stuff. Let's look at the conjugate prior again. No, it was earlier, wasn't it? We have to specify 4 numbers. I'm on equation 19 now on page 11. To use the conjugate prior in the Gaussian model with both mu and sigma squared unknown, there are 4 hyperparameters to specify. Each of them plays the role, the nu 0 and the kappa 0 play the role of prior sample sizes, respectively, for the information about sigma squared and about mu given sigma squared. And sigma 0 squared and mu 0 play the role, respectively, of prior estimates of each of those quantities. If I want to have a low information prior, then what should I do with those numbers nu 0 and kappa 0? If they represent prior sample sizes, then to create a low information prior, I should make nu 0 and kappa 0 both what? Rather small. They have to be positive for the thing to work, but I can make them small and as close to 0 as I want, and I'll get a proper prior distribution. And having done that, it doesn't matter very much what we put in for sigma 0 squared and mu 0. Things will just be driven by the data mostly rather than the prior. So, like it says on page 17, I don't know anything about what NB10 is supposed to weigh down to the nearest microgram or about the accuracy of the National Bureau of Standards measurement process. So I would like to use a diffuse prior for mu and sigma squared. And when I consider the meaning of the hyperparameters to provide little prior information, I want to choose both nu 0 and kappa 0 close to 0. If you ran them down exactly to 0, you'd end up with an improper prior that integrates to infinity. But choosing positive values as close to 0 as you like will yield a proper prior that is highly diffuse in both directions. So now if you go back to these updating equations and stick in kappa 0 equals close to 0 and nu 0 equals close to 0, then what happens is that the posterior mean will be just y bar, which is what you'd expect, and the posterior variance turns out to have a simple expression as well. So when we plug in kappa 0 and mu 0 close to 0, what we find is that the marginal posterior for mu, given the data and the Gaussian assumption, was exactly equal to the t-distribution on n degrees of freedom, centered at y bar, and having as its precision parameter, its scale parameter, n minus 1 s squared over n squared. But if you look at that, when n is large, n minus 1 over n squared is essentially just n. And we know that when n is large, the t-distribution on n degrees of freedom is essentially the same as the normal. And so the marginal posterior for mu, given the data and the Gaussian assumption, is just like a normal curve centered at y bar and with standard deviation s over the square root of n. So basically, with diffuse prior information, the Bayes answer is the same as the frequentist answer, namely, you would start with a t interval and go the sample mean plus or minus a t number times the usual standard error s over the square root of n either way. And with 100 observations, to the right t number is 1.98. I think there's a typo in equation 28, I think that should be the t curve on n minus 1 degrees of freedom. Let me look back. U sub n. No, it should be approximately t on n. Okay, anyway. Okay, and so that's our answer. Both frequentists who assume the Gaussian model and Bayesians who assume the Gaussian model with the diffuse prior would conclude that NB10 weighs about 404.6 micrograms below 10 grams, give or take about 0.65 micrograms. So we're down to a pretty small uncertainty band when you're thinking about the fact that their weighing process is accurate to about 5 or 6 micrograms each time it's weighed. Now, my second question was, is it true, is it likely, based on the data, that the true weight of NB10 is less than some value like 405.25? The Bayesian approach has a direct answer to that because we're allowed to make direct probability statements about anything. So I have a posterior for mu, which I just worked out as approximately normal, centered at y bar, and with variance given by s squared over n. And so I just asked the normal curve, what's the probability of getting a value less than 405.25 in that particular posterior? So there's a little sketch of it on the next page. I draw the marginal posterior for mu, and I find that place 405.25 as a vertical line in there. And I look up the area under the normal curve. To the left of that, the normal curve with the mean of 404.5 and a standard deviation of about 0.65, and it turns out to be about 85%. So your betting odds, if you were going to bet with somebody about whether the true weight really is less than 405.25, you would say that you would favor that proposition at betting odds of about 5.5 to 1, because the odds would be 0.8, the posterior odds would be 0.85 over 0.15, and that's about 5.5 to 1. So that's moderately strong but not overwhelming evidence that the statement mu is less than 405.25 is true. That proposition is true. From the frequentist point of view, we're not allowed to talk about that, you remember, because mu is a fixed unknown number that either is less than 405.25 or not. But we can come fairly close to the Bayesian analysis here in the special case where the statement about mu is a one-sided sort of statement. You can do a hypothesis test of the null hypothesis that mu really is less than 405.25. And when you work out the p-value, you approximately get about 0.15, which handily turns out to be exactly what you get by calculating 1 minus the Bayesian posterior probability that that statement is true. People like to think of the p-value as standing for the probability the null hypothesis is false. And in fact, in other words, 1 minus the probability that it's true. In the Bayesian approach, in the frequentist approach, you're not allowed to think about it that way. But in the Bayesian approach with diffuse prior information and a large sample size, that's a perfectly reasonable thing to do. And you see there's a direct connection between the Bayesian posterior probability and the p-value. As long as you put the mu less than 405.5 in as the null hypothesis, then there's this nice direct connection. Frequentists would say, since that p-value is 0.15, frequentists would say, well, insufficient evidence to reject the null at the usual significance levels. Okay, it's still true that you have Bayesian posterior odds of 5.5 to 1 in favor of that null hypothesis. So saying there's insufficient evidence to reject it, well, anyway, you see whether that's a satisfying conclusion or not. And we see the connection between the p-value and the posterior probability. This turns out to arise only because the null hypothesis is one-sided. People who like to test point nulls of the form mu is exactly equal to some number will be in for a rude shock when they try to think about that from the Bayesian point of view. And I'll have a lot more to say about that later on. In my opinion, sharp null testing that mu is exactly equal to some number, is almost always completely silly. And I wish that our textbooks were not filled with utterly silly examples of doing it. And I'll say more about that later. But if you look at the logic of the frequentist hypothesis test, you can see that it's trying to answer a completely different question that may or may not be the right question. In Bayesian language, it tries to talk about what the probability behavior is of y bar if you knew what mu was, whereas, of course, what we really want to know from an information processing point of view is your information about mu given what y bar was. So in effect, the frequentist approach is doing something like a conditional probability calculation, but it's conditioning in the wrong order. No wonder it can sometimes produce silly answers. Okay, the third thing is I asked what was the predictive distribution of a future observation. And so there's the actual answer. But we know already for n large and prior sample sizes close to 0, this is approximately a normal distribution with mean y bar and variance s squared. In other words, a posterior predictive interval would just start at the sample mean and go about 2 sample standard deviations either way, and that brings you from 392 to 418. Frequentists have a little more trouble talking about posterior predictive intervals, especially when there's lots of unknown parameters floating around, but that's a very natural thing. Of course, they can't call it a posterior predictive interval because that would make them Bayesian, but they have trouble talking about predictive intervals for problems that are any more complicated than one parameter at a time. So the Bayesian story is quite natural from that point of view. Now that I know what the predictive distribution looks like, I can do something like what I showed you before, except I'm not going to go to the trouble of jackknifing all the 100 points. I'm going to go ahead and simply plot the 95% posterior interval based on the whole data set, and then locate each of the actual data points in that plot, and you can look with me and see if they look extreme or not. So I've plotted the standardized NB10 values, so I subtracted off their mean and divided through by their standard deviation to standardize them. And then I've plotted that against a standardized version of this predictive distribution. So the points in the distribution, in the actual data set, show up as little dots that are hard to read. Sometimes they look just like smudges or photocopying blips if you were photocopied this. But you can actually see them. And the things that look like vertical lines are places where there were repeat observations. Does it look to you as though those particular 100 observations could comfortably have come from that particular standard normal distribution? Yeah, exactly. And we can see rather more sharply how worried we should be. The smallest observation in standard units is minus 4.6. That would never happen with only 400, or rather with only 100 observations from a Gaussian. The second biggest observation is plus 2.8. That would just about happen with 100 observations. And the biggest observation is plus 5.0, which would never happen with only 100 Gaussian observations. So with the symmetric heavy tails indicated in these plots, the empirical CDF looks quite a bit like that of a T distribution with a rather small number of degrees of freedom. And so that suggests writing out a new model, like I showed you a minute ago, where let's build a model in which we think of the data as like draws from a T distribution with unknown degrees of freedom, and that degrees of freedom parameter will play the role of the shape of the distribution, how heavy the tails are. And this is an example, our first example of a very natural thing that Bayesians do all the time. When you write down an initial model and you discover it doesn't fit very well, a very natural thing to do is to find a bigger model of which the first model is a special case, and embed your previous analysis in that bigger analysis. So for example, in the Poisson example I showed you before, if we thought that Poisson was not such a good model for the data because the variance to mean ratio was really bigger than 1, then we could embed the Poisson in the negative binomial as a special case of the negative binomial, and then look and see if the model fit is better inside the bigger model class, and if it is, then of course we stick with that particular bigger model. Here, you probably remember that the normal distribution is a special case of the T distribution with very large degrees of freedom. And so if we start with a normal distribution and it doesn't look good on grounds of heavy tails in both directions, then why not embed it in the T family with unknown degrees of freedom and ask the data what the degrees of freedom are. And if at the end of this exercise, the posterior distribution on the degrees of freedom comes out centered on values like 400 or 500, then that would be the Bayesian way of saying, well, this data set is pretty Gaussian after all. Whereas if the posterior on nu came out centered on values close to 0, as it's going to, as you'll see, very small degrees of freedom, that would be a way of saying the normal is a silly model for this data set, and we had better go with something with heavier tails. And so as soon as you write down this bigger model that has 3 parameters, the mu for location, the sigma for scale, and the degrees of freedom nu for tail weight, you start looking for a conjugate prior, and you find there is none. You can begin writing down some things that are conditionally conjugate for mu and sigma squared, but there is no conjugate choice for the degrees of freedom. There is no conjugate prior in this model. So whereas in all our previous examples we found that conjugate priors did exist, and the question was just, could our prior information be quantified through a conjugate prior? This is actually our first example of a model where there is no conjugate prior. And so we can't use conjugate updating as our way of doing the calculations in this model. And in fact, there's no really good way to do it except using markup chain Monte Carlo. And so that's, well, I'll be showing the NB10 data set as an example, as our case study continuation in the MCMC section. I owe you a little description of the exponential family because I mentioned it in the context of that theorem by Percy Diaconis and Don Ilvasacker. Back in the 1940s, these guys named Koopmans and Darmois, I believe working independently, noticed something interesting, which was that they tried to write down all the usual standard sampling distributions that anybody ever used, and they tried to look around and see were there any common features to all these distributions. Because if they all satisfied some basic common features, then we could think of all of them as special cases of some big umbrella and then try to do inference in that big umbrella. And so by doing that, they invented this thing called the exponential family. And so there are several different definitions of it. I'll show you the first one here now. Suppose you start with one data point at a time, a sample of size 1, taking the value y1, and you have a k-dimensional parameter vector, theta 1 through theta k. People say that the marginal sampling distribution of y1 by itself belongs to the k-dimensional exponential family if it can be expressed in a very special form. And so let's look at the right-hand side of 30 and see what it means. In order for this to be part of the exponential family, you have to be able to write the sampling distribution as the product of a bunch of stuff. So let's look at it. First, there's a normalizing constant that doesn't depend either on y1 or the parameters, c. Then the next thing in the product has to be a function of the data values alone, not depending on theta. Then the next thing in the product has to be a function of theta alone, not depending on y. And then the part of the sampling distribution that depends both on theta and on y has to have a very special form. It has to look like e to the sum of a bunch of stuff. And each of the things in the sum is itself a product, and it's a product of two things. A function of involving only the parameter vector, which here I'm calling, phi j of theta when we have j equals to 1. Times a function only of the data, which here I'm calling h1 of y1 for the first term in it, and so on out to the kth term. This is all very complicated looking, but I'll explain in a minute why this is actually pretty natural. And this is the right form for the exponential family whenever the data values are in that range space script y for where the different values for y can live, and then the sampling distribution is 0 otherwise. And then you remember that distinction I drew a while ago. If it turns out that the range of possible values for y depends on the parameter vector we say we're in a family called a non-regular parametric family. Otherwise, we talk about it as a regular family. And having discovered what these functions of the parameter vector are, phi1 of theta down through phi k of theta, they are referred to in the jargon as the natural parameterization of the exponential family. And they might not just be the same as theta itself. In other words, phi1 down to phi k might not just be the identity functions. I'll give an example in a minute. And so, of course, since the data are IID from that sampling distribution, then the joint distribution looks like this. It's a product of the marginals. And look, it looks just like the previous thing, except now the e to the stuff has a double sum in it. And I can take the product of the f1 of yi's and think of it as the function only of the data. And I can take the previous g1 of theta raised to the nth power and think of it as the function only of theta. And now what happens in the exponentiation part is that everything has to look like e to the stuff. And the stuff is always the following double sum. First, you set j equal to 1. And it says, OK, find your function phi1 of theta and multiply that by what you get by adding up h1 of yi across all the yi values. Then do that for phi2 and so on down to phi k. Again, a big mouthful, and why would anybody care about this? But there it is. So here's the alternate definition of it. Given data that follows the exponential family, it's expressible, the entire joint distribution is expressible as a single number that acts like a normalizing constant times a function only of the data vector times a function only of the parameter vector times that e to the stuff. And right away, when you look at that, the vector of the form summation of the values h1 of yi, summation of h2 of yi, dot, 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 down to summation of hk of yi, right away you see that that's a set of sufficient statistics under this model because the likelihood function depends on the data vector only through those functions. So that's a nice thing about the exponential family. When you express your sampling model in its form, right away you get an obvious set of sufficient statistics. You can just pick them right out like that. And the other cool thing about the exponential family is that if your sampling distribution is from it, then you don't have to search very hard for a conjugate prior because you can just look at the form of the exponential sampling distribution and see what the prior has to look like. And so if you can fit your sampling distribution into the exponential family, 32, then the conjugate prior that goes along with it has to look like equation 33. Now, this has all been very abstract. Let me show you some examples. That would be even simpler. If the same function h applied across the whole thing, then that would be like a much lower dimensional sufficient statistic. That's right. This stuff unfolds most naturally if we look at examples. So bear with me. That's an ugly formula 32 and an ugly formula 33, but they actually make good sense when you start specializing them into particular examples. Anyway, if you take that as your prior and multiply through with that sampling distribution stroke likelihood, you get equation 34 is the posterior. And if you stare at that for a moment, that indeed does have exactly the same functional form as that prior. So that demonstrates conjugacy. So here's some examples. Let's go back to our heart attack case study with 100 binary observations. And our model was that the data are conditionally IID Bernoulli theta. And we also saw that that applied to the binomial where we just looked at the sum. So the likelihood function is expressible as theta to the s times 1 minus theta to the n minus s. To see whether that's a member of the, in this case, one parameter exponential family, because we only have one unknown, I have to write it in a special form. You remember what the form was? I have to write it as a function only of the data, which might just be the constant function, times a function only of the parameters, times e to the stuff, and the stuff always has to look like a sum of terms, each of which is a product of stuff that depends only on the parameter times stuff that depends only on the data. So let's see if we can fiddle around with this form here and see. Well, at the moment, that looks nothing like, the first line of equation 35 looks nothing like what I need it to look like to be a member of the exponential family. But now let's try exponentiating logarithms of it. Well, first of all, let's pull out the part that depends only on theta. The theta to the s part depends on both of them, and the 1 minus theta to the minus s part depends on both of them as well. But look, there's hidden inside there a little thing of the form 1 minus theta to the n. So let's pull that out in front, and that becomes my g function. G of theta equals 1 minus theta to the n. And what's left is theta over 1 minus theta to the power s, and that's supposed to be expressible as e to some stuff. And so let's take a minute and see what that would be. So if that's supposed to be expressible as e to some stuff, then theta over 1 minus theta to the s can be written as e to the log of theta times 1 minus theta to the power s. Right? You can always e and log something and get back the same thing you had. And you remember how logs work. The logarithm of something to a power, you get to bring the power down in front. So that's the same as e to the s log theta over 1 minus theta. And check it out. There it has the exponential family form. h1 of the y vector is the sum. Needs to be a little higher. h1 of the y vector is the sum. And the function that's the function of the parameter is just not theta, but log of 1 minus theta over log of theta over 1 minus theta. So we've been able to trick the likelihood function or sampling distribution in the Bernoulli binomial model into the exponential family form. And as a by the way, this thing here was called the natural parameter of this family. And those of you who've seen this sort of thing before, in what kind of analyses do we work with things like log of a probability over 1 minus the probability? That's right. That's just logistic regression right in front of you, right? The left-hand side of the logistic regression model goes log of P over 1 minus P is expressed linearly in terms of the predictors and so on. So we see right there in writing things out as the exponential family that theta, the success probability, is not actually the natural scale in which to think about it. Instead, it's log of theta over 1 minus theta. And you'll notice that that's an interesting transformation. Theta lives only between 0 and 1. Theta over 1 minus theta, if you think about it, lives somewhere between 0 and plus infinity. And the logarithm lives on the whole real line. So this is a parameterization. It's a transformation of theta that has forced the parameter to live on the whole real line. And that, in some sense, is more natural than looking at it on a restricted scale. So that could be thought of as the way that this came about. So that just says over again what I found here. So we've got the exponential family with one dimension, k equals 1. G of theta is 1 minus theta to the n, and the natural parameterization is the logit, as people call it. That's another name for that. And the sum of the y's is sufficient for theta. And right away, our previous equation says that the conjugate prior for the Bernoulli binomial likelihood has to have that form. C times 1 minus theta to the n times pi times tau 0 e to the tau 1 times log of the parameter. And you can push that around for a little while, and it comes out the beta distribution, which we already knew was the right conjugate prior, but now we can see that we're getting the right answer from it. What's that? Oh, damn it. I've been talking from... Oh, I'm sorry. The screen, what would you just say? Okay, good. There's the conjugate prior for the Bernoulli binomial likelihood. We just used that equation I showed you before, equation 33, and stuff in all that stuff we just learned about the conjugate, the exponential family, and presto, out comes the beta distributions. So if you hadn't known it was conjugate before, you can use this general theorem. Just express your sampling distribution as a member of the conjugate, as a member of the exponential family, and then bing, right out of that comes what the conjugate prior has to be. Here's an example of a non-regular exponential family. And I've asked you to think about this model in problem set 3. Suppose that a reasonable model for the data is to take the observed values, yi given theta, to be conditionally IID from a uniform distribution on 0 to theta, where you don't know what theta is. And I'll give an example of that right now. If we look at, that might sound like a weird model, but it comes out naturally in problems actually this problem is in a field that none of you in the room are in, but I'll just give you an example. It's in the field of paleobotany. The way paleobotanists estimate when in the remote past a given species became extinct, they do that by taking core samples that are cylindrical in shape, and they bore down vertically well below the Earth's surface, and they look for the last occurrence of the species in the fossil record as measured in meters above the point capital P at which the species was known to have first emerged. And if you let the y sub I stand for your random sample of such distances at a bunch of different randomly chosen points on the surface of the Earth, the model yi given theta is IID uniform 0 theta emerges directly from natural assumptions. And so while this might seem a strange model, it comes out directly in problems involving sampling of this kind where you're drilling down into the Earth. And in this model, the unknown theta can be used through carbon dating to estimate the species extinction time. So it's a very natural context. And here we have it. And so that would be what you'd have. The marginal sampling distribution for any one observation just looks like 1 over theta for the y value living between 0 and theta, and 0 otherwise. And we could use the indicator function notation. I of a equals 1 if a is true and 0 otherwise. And so I could use the indicator notation 1 over theta, indicator of yi in the interval 0 theta. Now this is a nasty model because it's not regular anymore. Here, the range of possible values the data could have depends upon the parameter. Explicitly, it's right there in the model that to know where the y values could live on the number line, you have to know what theta is. You cannot, according to this model, get a y value bigger than theta. So this is a range restriction parameter. And parameters like that are fundamentally different from location and scale parameters, things like the mean and the variance in the normal model. And they're also fundamentally different from shape parameters, like the degrees of freedom in the T model. You can, in fact, poke this particular situation into the exponential family form. So it is a member of the exponential family, the one-dimensional exponential family, but only when you choose the set of possible values for the y variable to depend on theta, and that's what makes it non-regular. And if you work through the details in this problem here, you will discover that all manner of weird things happen. Let me show you, for example, what the likelihood function looks like in this model. After some thought about it, you discover that it has to look like that. You're able to express the likelihood function as the 1 over theta, the product of terms of the form 1 over theta times the indicator that yi's live between 0 and theta. And now if you think about that carefully, the only way that indicator function can be true across all of the data values is if, of course, all of the yi's are between 0 and theta. And the only way that can happen is if theta is greater than or equal to the largest of the yi values. So let's call m the maximum or the largest of the yi values. If you knew that the largest of the yi values was less than or equal to theta, that would imply that they were all between 0 and theta. And conversely, if you knew that they were all between 0 and theta, then the maximum has to be less than or equal to theta. So that's actually an if and only if. And now if you plot that function, theta to the minus n, indicator of whether theta is bigger than or equal to m, you get a very weird looking likelihood function, which is 0 on the interval, the interval for theta all the way down to 0. And then it jumps up to a spike of height theta to the minus n at the maximum of the data values, and then it falls off monotonically from there. And so our ordinary methods of finding the maximum likelihood estimator would involve differentiating this function and setting it equal to 0. And you can see that that doesn't work worth a damn in this problem because the function is not differentiable at the most interesting point. In fact, we can maximize this function by inspection, right? There's the likelihood function. So where does its maximum occur? Right there in the picture, it occurs at m. And so we see right away that the maximum likelihood estimate in this model is the maximum of the data values. However, the large sample behavior of the maximum likelihood estimator is really, really different in models like this. And what you do when you work it through, it turns out that the conjugate prior is a member of what's called the Pareto family of distributions. And the posterior is then, of course, also Pareto. And you get very strange looking pictures like this, where the prior is the Pareto on the left, that's the shortest one. And the likelihood is the Pareto in the middle, that's in between the two. And the posterior is the tallest of those two. So actually, this is an odd setting in which the posterior doesn't actually behave quite like a weighted compromise between the two priors. So weird looking prior to posterior updating plot. And even more strangely, when you work out the posterior variance, you discover that the formula for the posterior variance goes down. What's our usual thing? The variances all look like blah, blah over n, right? So that the standard errors look like some other blah, blah over square root of n, right? But look at that expression and simplify it, thinking of it as something where n gets big. You've got a single n in the numerator, and you've got n squared times n in the denominator. So this thing behaves not like order 1 over n, it behaves like order 1 over n squared. In other words, this is an amazing model in which your uncertainty on the scale of the data, by taking the square root of that, goes down not at a square root of n rate, but at a rate of n. It goes down very, very, very fast. So whenever you work with models with range restriction parameters, the large sample behavior is completely different. And in particular, what this is saying is that it's much easier to learn about a range restriction parameter than it is to learn about a location parameter or a scale parameter. You learn at a rate which is vastly faster. And that should make some sense, right? Because what you're getting from the data is that anytime you get an observation that's bigger than any previous one, you already know that theta has to move quite by however much bigger that observation is than the previous ones. And so every single observation has a chance to change your best guess for theta by a large amount, and that means that you are getting a lot of information from each data point, and that means that your uncertainty goes down at a faster rate. Quite remarkable. Okay, and as a final example of this sort of thing, here's another example. People sometimes use models for data that behave like truncated distributions with unknown truncation points. And I'll give you another example. People sometimes, well, in fact, that's what I'm about to show you is sort of in that family. So let's go over here for a minute. Sometimes people write, we're going to talk for a minute about the log normal distribution. So I need to remind you about the log normal distribution. This turns out to be a good distribution to know how to work with. First of all, it turns out to be badly named, I'm afraid. Let's see. W is a draw from a log normal distribution with parameters mu and sigma squared. This is the usual way people write it. If and only if, what does it mean? Anybody recall? If the logarithm of W follows a normal distribution. If and only if log W follows a normal distribution. And in fact, the mu and the sigma squared refer to the parameters of the thing on the log scale, not on the raw scale. So that's the usual way people write down the log normal distribution. So that's actually a bad name for it, because actually the way you get W is you exponentiate a normal, not log it, right? And so it should be called the exponential normal distribution. But somebody got it wrong about 120 years ago. This is when this distribution was first looked at, and they called it the log normal distribution, and we're all just stuck with it now. Okay? All right, well, that's, and what's that shape going to look like? If you take a normal and exponentiate it, what sort of distributional shape are we going to expect for W? Is it going to be symmetric or have a long left or right-hand tail? Can you tell? If you start with the normal and exponentiate it, so here's the normal down here, running from maybe -2 to +2. This is our, this is our log W down here. And if I exponentiate stuff from -2 to +2, first of all, exponentiating it, all the new values have to be what? Have to be positive, have to be non-negative. And some of them can get really big, right? Because you're exponentiating stuff in the right tail. So the log normal has a very long right-hand tail. That's your basic shape for the log normal. So this is the log normal shape. But sometimes people fit a distribution where the place that it starts is a third parameter. And so you've got a mu here and a standard deviation sigma down here, and you have a parameter A that says this is the place on the number line where the data starts. And so that becomes a 3-parameter log normal where you have unknown location on the log scale, unknown scale on the log scale, and unknown place where the data starts on the data scale. And that's another one of these range restriction parameters, right? Because the data can't ever be smaller than capital A. And so what will happen in this model is you learn about mu and sigma at our old snail's pace of order 1 over the square root of n on the standard error scale, but you learn about A at the 1 over n rate. So that's going to be weird where 2 of your parameters, it takes you much longer, much more data to learn about them than the other one. That comes up sometimes. Okay, and returning to the, returning here, what we've just discovered is that on the variance scale, the posterior variance goes down like order 1 over n squared, which is astonishing compared with the usual order 1 over n. I spent some time once trying to figure out if there was any way to improve the rate at which we could learn about other parameters like mu and sigma squared by somehow doing something to them that made them into range parameters, range restriction parameters, and then learned about the new thing in the faster rate. Turns out you can't do it. Other people have, of course, thought of that before me, and there are papers written showing, with theorems showing you can't do it. The only way you can learn faster than C over the square root of n in regular parameters is to find C1, let's call it, over square root of n for estimation method 1, is to find another estimation method that learns at a rate C2, excuse me, learns at a rate C2 over square root of n where C2 is smaller than C1. All you can do, you're stuck with the square root of n part of things for regular parameters, but you can find a new way to possibly to look at the data in which the C2 in the numerator is smaller than the C1. But I think I actually told you about this last time as well. Fisher showed that the maximum likelihood estimators have the wonderful property that among all estimators that do behave like normal curves in the limit as n gets big, the C in the numerator of that C over the square root of n for the maximum likelihood estimator is the smallest possible. So you can't do any better than maximum likelihood estimators from a frequentist point of view. And the reason for that is obvious. Fisher didn't know the theorem at the time, but as I've told you, we have theorems now that show that Bayes' theorem is an optimal information processing, and the maximum likelihood story is an approximation to Bayes with large data. And Fisher was only thinking about large data when he did that observed information stuff. So he was just reinventing the optimal information processing of the Bayesian approach. Now, for an exponential family example with more than one parameter, we could take the Gaussian with both things unknown. And if you shove it around for a while, you can show that it is of the form, the exponential family form, in which the ingredients are as I've given you here. And the sum of the y's and the sum of the y squares are together a sufficient statistic. Or equivalently, you could rewrite that as y bar and s squared as being sufficient. They have the same information content as the sum of the y's and the sum of the y squares. And some unpleasant algebra then demonstrates that an application of that previous little theorem about conjugate priors leads to the thing I showed you before as the conjugate prior when both are unknown. So everything is nice and internally consistent. I would now like to take a few minutes. You've begun to hear me already. Actually, it's time for our next break, so let's stop. And when we come back, I will deliver a sermon on why hypothesis testing is bad.